Have you ever just looked up at the night sky and felt that, I don't know, that ancient, irresistible pull,
Yeah,
that deep curiosity about what lies beyond our world? It's a feeling that connects us, right? Across millennia, across cultures.
it truly is. Um, from the moment humans could look up, really, they began asking questions. And that persistent wonder has driven this incredible journey of discovery, constantly reshaping how we see the universe.
Absolutely. And today we're taking a deep dive into that epic journey. Our source material for this exploration comes from excerpts from the Astronomy Book, which is, well, a fascinating look at the history, the key concepts, and the brilliant minds that have shaped our view of the cosmos above us.
Think of this deep dive as your shortcut. We're going to try and distill the most impactful insights and maybe even some surprising facts from these pages to give you a clear, well-informed picture of how our cosmic perspective has evolved. We'll go from, ancient observations right up to the cutting edge of modern astronomy.
That's our mission then, to trace the evolution of our understanding, guided by the details in these excerpts, and see how our view of the universe has transformed. From something seemingly small and Earth-centered to, well, something unimaginably vast and dynamic.
So what kind of scope are we talking about here? The astronomy book covers the sheer vastness of the universe and, well, our tiny place within it. It details how our view has changed not just gradually, but often, like, dramatically over centuries.
And crucially, it presents astronomy not just as charting stars, putting dots on a map of the sky, but as this incredibly dynamic, living field. It's constantly being reshaped by new technology and fresh insights, pulling together threads from history, physics, even chemistry and biology. The sources mention fields like astrochemistry and astrobiology emerging, showing just how broad this discipline has become.
Yes. The excerpts give us this beautiful historical progression. We start with the earliest human records, move through pivotal periods like the telescope revolution, and into the age of astrophysics. It really highlights that knowledge isn't just accumulated, it's built upon, sometimes overturning previous ideas entirely, sometimes adding subtle but crucial corrections.
And the topics covered are immense. We're looking at understanding the fundamental properties of stars, the intricate mechanics of our own solar system and those beyond, the structure and evolution of galaxies, and wrestling with the fundamental nature of the universe itself. It's a journey that just keeps expanding as our tools and understanding improve.
Okay, so let's unpack this journey, starting right at the very beginning, with those early observations and the models humans first built to make sense of the cosmos.
Where else would we start? Astronomy has roots that go back further than written history. The sources point to archaeological evidence from prehistory, things like megalithic structures, may be aligned with celestial events, suggesting that even very early societies use the predictability of astronomical phenomena.
Well, the precise knowledge of prehistoric peoples is open to interpretation from these structures, of course. But the oldest written astronomical records we have, they come from Mesopotamia, dating back about 5,000 years. And these early observations weren't just academic, they had incredibly practical applications.
That's a key insight right there, isn't it? Beyond simple wonder, the predictability of celestial cycles was absolutely vital for timekeeping, for navigation.
Crucially important. I mean, before atomic clocks or GPS, observing the heavens was the way to measure time accurately and figure out your location. This practical need was so fundamental that governments established national observatories, often starting in the 1670s, precisely to serve as the keepers of time and provide navigational data. For centuries, astronomers were essential for daily life and global exploration.
Imagine that for much of history, your ability to keep time or sail across an ocean depended on the work happening inside an observatory. It really highlights the foundational role astronomy played.
And while these practical observations were happening globally, the dominant cosmological view in the Western world, from about the 4th century BCE until the 16th century CE, was, well, the geocentric model. This held that Earth was stationary and sat at the absolute center of the universe, with everything else revolving around it on perfect crystalline spheres.
And this wasn't just pulled out of thin air, right? There were seemingly logical reasons for it. They dismissed ideas like Earth spinning because, intuitively, if the Earth were rotating rapidly, wouldn't objects just get thrown off? That seemed like a solid argument against Earth's motion if you didn't understand the physics involved.
It seemed reasonable based on everyday experience, sure, but it's vital to see that other perspectives existed. The sources mention that in India, the astronomer Aryabhata, around 499 CE, proposed that the apparent movement of the stars was caused by Earth itself rotating, not the stars revolving around a stationary Earth. This was a counterintuitive idea at the time, but, closer to our modern understanding.
And Chinese astronomers were making sophisticated observations too. Figures like Zhang Heng in the 1st to 2nd century CE understood that the moon's light was reflected sunlight.
Building on that, Shen Ku in the 11th century used observations of the moon's phases to argue that both the moon and the sun must be spherical. Seeing the crescent moon, for instance, showed that light wasn't evenly distributed across a flat surface, implying roundness. Clever stuff.
Calendar systems across different cultures were another testament to early astronomical skill. The traditional Chinese calendar, formalized in the 1st century BCE, used a solar year length of 365.25 days.
What's fascinating is that this was established about 50 years before Julius Caesar adopted the exact same length for the Roman Julian calendar. Later, in 1276, Guo Xiaojing created the Shoshi calendar, achieving an incredible accuracy of 365.2425 days per year, which matches the year length of the Gregorian calendar, which wasn't introduced in Europe until, 1582. This kind of precision, achieved with instruments like a massive sundial gnomon, is just astounding.
Early astronomers also meticulously cataloged stars. Hipparchus, around 130 BCE, created a catalog of over 850 stars, measuring their positions and brightness.
Yeah, and this work was carried forward and incorporated into Ptolemy's monumental work, the Almagest, around 150 CE. Ptolemy's geocentric model and his star catalog became the standard astronomical text in the Western world for over 1,000 years. It was the reference.
Even centuries later, corrections were being made to Ptolemy's long-standing data. The Mongol ruler Ulugh Beg, himself a brilliant astronomer and mathematician, established a major observatory in Samarkand in the early 15th century.
Yes, Ulugh Beg and his team compiled a new star catalog, significantly more accurate than Ptolemy's. It's a testament to the continuation and refinement of astronomical work across different cultures. Though, as the sources note, his dedication to science didn't save him from political intrigue. He was tragically beheaded by his own son shortly after becoming ruler. A bit grim.
A stark reminder that the pursuit of knowledge didn't always lead to a peaceful life. We should also acknowledge the vital role of Arab scholars during the European Middle Ages. The sources mention Gerard of Cremona translating key Arabic astronomical texts, including Ptolemy's Almagest, into Latin in the 12th century, which was crucial for transmitting classical knowledge back into Europe.
And even within that body of knowledge, critical thinking existed. Ibn al-Haytham, an Arab scholar around 1025, wrote a critique of the Ptolemaic model, pointing out its increasing complexity with all the epicycles and deference needed to explain planetary motion. Even then, some saw the elegance issue with the geocentric system. It was getting messy.
Which brings us to a truly revolutionary period, the telescope revolution, roughly spanning from 1550 to 1750. This is where our ability to see the universe changed fundamentally.
Before the telescope, though, we have the last great astronomer of the old guard, the Danish nobleman Tycho Brahe. Recognizing the limitations of previous observations, Tycho built massive, highly precise instruments pre-telescope, remember to measure star and planet positions with unprecedented accuracy.
He amassed a vast amount of data, far more precise than Copernicus ever had access to, and that data would become invaluable for his successor. Tycho was working in a time when the Aristotelian idea of fixed, unchanging heavenly spheres was still dominant. But in 1572, he saw a new star appear, a supernova in Cassiopeia.
Using his precise measurements, Tycho proved this new star wasn't an atmospheric phenomenon below the moon, as Aristotle suggested for anything that changed. Nope. It was far away among the supposedly fixed stars. This directly challenged the idea of an unchanging celestial realm. Big deal.
Tycho also grappled with the structure of the solar system. He admired Copernicus's sun-centered model, but couldn't detect the expected stellar parallax that apparent shift of stars as Earth orbits. We'll get back to that.
Yeah.
He also still believed Earth was stationary.
So he devised his own model, the Tychonic system. Earth was still central and stationary, right? But the other planets orbited the sun, while the sun and moon orbited the Earth. It was a clever attempt to combine the best parts of both models based on the data he had. Kind of hybrid.
But the real game changer arrived around 1608, the invention of the telescope. Suddenly, the distant sky was within closer reach.
And the person who truly leveraged this new tool was Galileo Galilei. He didn't invent the telescope, but he improved its design and, crucially, was one of the first to systematically point it at the sky and understand the profound implications of what he saw.
His observations were revolutionary. Seeing Jupiter's 4 largest moons, that was direct evidence that not everything orbited Earth. These moons orbited Jupiter. It showed there were other centers of motion in the cosmos.
He also saw features on the moon mountains and craters showing it wasn't a perfect smooth sphere. And he observed sunspots, showing the sun wasn't an unblemished perfect orb either. These observations directly contradicted the Aristotelian view of perfect celestial bodies, just blew it apart.
It's no surprise many were skeptical. Some critics initially claimed the moons of Jupiter were just like optical illusions caused by Galileo's telescope lenses.
But as other astronomers acquired telescopes, like Thomas Harriot, Joseph Gaultier, and Nicolas Claude Fabry de Peresque, they confirmed Galileo's findings, cementing the reality of these new discoveries. There was even a dispute over who saw Jupiter's moons first with Simon Marius, highlighting the excitement and competition of the era. Everyone wanted in.
The telescope also revealed that stars weren't all fixed and unchanging. David Fabricius, in 1596, discovered the variability of the star Miracetti, showing its brightness changed over time.
This was another blow to the idea of fixed stars. Later astronomers like Geminiano Montanari and famously John Goodricke and Edward Pigott in the late 18th century discovered other variable stars, paving the way for understanding their pulsating nature and eventual use in measuring cosmic distances, which turned out to be super important.
A significant event during this period was the transit of Venus across the Sun's face. Jeremiah Horrocks, a young English astronomer, predicted the 1639 transit using his corrections to Kepler's tables.
Horrocks and his friend William Crabtree became the first people to witness this transit, independently observing it by projecting the sun's image using a helioscope, which is basically a safe way to look at the sun through a telescope. This was a meticulous observation that hinted at the potential of telescopes for precision measurement.
Other astronomers were busy discovering new solar system objects, too. Cassini discovered several moons of Saturn and Jupiter, dramatically increasing the number of known satellites at the time.
And the sources briefly note the diversity of moons, some large ones likely formed with their planets, others probably captured asteroids. It also touches on the puzzle of Earth's large moon and the lack of moons around Mercury and Venus, questions still explored by planetary scientists today. Lots still to figure out even close to home.
All these celestial movements begged for an explanation, and that explanation came from the fundamental force we call gravity.
And the key figure here is Isaac Newton. But his work definitely stood on the shoulders of Johannes Kepler. Kepler, using Tycho Brahe's incredibly precise data, especially his measurements of Mars's orbit, spent years trying to find a mathematical description of planetary motion. Years of number crunching.
And he had a profound breakthrough. His first law stated that the orbits of planets aren't circles, as previously assumed, but ellipses, with the sun at one focus. The other focus is just empty space.
His second law explained that planets sweep out equal areas in equal times, meaning they move faster when closer to the sun and slower when farther away. His third law provided a powerful mathematical link between a planet's orbital period and its distance from the sun. The square of the period is proportional to the cube of the average distance. Really elegant.
It took Kepler time to confirm these laws for all the known planets. His third law appeared in his 1619 book Harmonices Mundi, which also contained his somewhat less scientific musings on astrology and planetary music. A man of his time.
It's interesting that while Kepler accurately described planetary motion, he didn't know why they moved that way. He speculated about magnetic forces or even celestial angels pushing them. The unifying concept of gravity was missing.
And that's where Newton's genius came in. He realized that the same force making an apple fall from a tree was keeping the moon in orbit around Earth and the planets in orbit around the sun. Gravity was a universal force acting between all objects with mass. It connected everything.
His monumental work, Principia, published in 1687, presented his laws of motion and universal gravitation. This book provided the mathematical framework to explain Kepler's laws from first principles and calculate the orbits of comets.
Huge. We owe a debt to Edmund Halley for encouraging Newton to publish Principia and even funding its printing. Halley himself used Newton's methods to predict the return of the comet that now bears his name.
Despite this incredible breakthrough, Newton was famously humble about the cause of gravity, stating he wouldn't frame no hypotheses about it. He described what gravity did, but didn't pretend to understand why masses attracted each other. Still a deep question, really.
Measuring the strength of this universal force precisely was the task of Henry Cavendish in 1798. Using a delicate torsion balance, he measured the gravitational constant J.
His measurement was remarkably accurate for its time. The sources note that a modern measurement from 2014 differs by only about 1%. That's just testament to Cavendish's experimental skill. Incredible precision.
Gravity shapes our world in profound ways we often take for granted. It limits the size of land animals. The biggest creatures are in the ocean, where water buoyancy helps counteract gravity's pull. Makes sense.
And of course, it causes the tides. The gravitational pull of the moon and sun creates bulges of water on Earth's surface. Spring tides, the highest and lowest, occur when the sun, Earth, and moon are aligned, combining their pull. Neap tides, the least extreme, happen when they are at right angles. It's all gravity at work.
Newton's thought experiment, sometimes called Newton's cannon, is a great way to visualize escape velocity. Imagine firing a cannon from a high mountain.
Fire it slowly, and the cannonball falls back to Earth. Fire it faster, and it might enter an elliptical or even a circular orbit. Fire it fast enough at escape velocity, and it breaks free of Earth's gravitational pull entirely. This concept was vital for understanding orbits and eventually for sending spacecraft into space. Gotta beat gravity.
Newton's laws were also incredibly powerful for predicting the existence of unseen objects. The sources tell the amazing story of Urbain Le Verrier in 1846.
Leverrier noticed slight deviations in the orbit of Uranus, tiny wobbles that couldn't be explained by the gravity of the known planets. Using Newton's laws, he mathematically calculated where an unseen planet must be to cause those perturbations, just with math.
He sent his prediction to Johann Galle at the Berlin Observatory. Galle pointed his telescope to the exact position Leverrier calculated, and boom, there it was, Neptune. Discovered not just by looking through a telescope, but through pure mathematical prediction based on gravitational theory, a stunning triumph for physics.
So we moved from describing planetary motion to understanding the force behind it. But what about understanding the stars themselves? What are they actually made of? For a long time, astronomy was primarily about mapping their positions.
Yes, there was a sense that we could never know what stars were made of. Seems impossible, right? But that changed dramatically in the mid-19th century with the rise of spectroscopy analyzing the light from celestial objects. This technique essentially gave birth to the field of astrophysics.
It's a perfect example of how a new tool can completely open up a field of study. As the sources note, astrophysics became one of many branches of astronomy, alongside cosmology, planetary science, and new interdisciplinary fields like astrobiology and astrochemistry, showing how integrated the study of space has become. It's all connected.
So, how does spectroscopy work? The basic principle is simple. Pass light through a prism and it splits into its spectrum, its constituent colors, like a rainbow.
Early observers like William Hyde Wollaston and Joseph von Fraunhofer noticed dark lines, now called Fraunhofer lines, in the sun's spectrum. But it was Gustav Kirchhoff, working with Robert Bunsen, who figured out what they meant around the 1860s.
They discovered that hot, dense gas produces a continuous spectrum, like a rainbow. But if that light passes through a cooler gas, that gas absorbs light at specific wavelength.
These absorbed wavelengths show up as dark lines in the spectrum, and the pattern of lines is a unique fingerprint for each chemical element. Kirchhoff confirmed this by matching the dark lines in the sun spectrum to the emission lines produced by sodium in their lab. This was revolutionary. It meant we could determine the chemical composition of distant stars, just from their light.
This led astronomers like William Huggins to apply spectroscopy to stars and nebulae. Working with his wife Margaret and chemist William Miller, Huggins showed that stars were made of the same elements found on Earth. Not some weird celestial stuff.
Huggins also used spectroscopy to show that some nebulae were luminous gas clouds, not just clusters of stars, because their spectra showed emission lines, not just absorption lines. Though some lines in nebulae spectra remained a mystery, nebulum, until much later when they were identified as ionized oxygen. Took a while to sort that one out.
With this new tool, astronomers began the massive task of classifying stars based on their spectra. This happened primarily at the Harvard College Observatory under Edward Pickering.
Yes, Pickering hired a team of women, often called computers, to analyze thousands of photographic spectra. Amazing work. Among them was Annie Jump Cannon, who developed the stellar classification system still used today, OBAFGKM. This sequence is based on temperature, from the hottest O stars to the coolest M stars. Cannon personally classified an astonishing 500,000 stellar spectra. Just incredible dedication.
Other key women in this effort included Williamina Fleming, who developed an earlier classification system, and Cecilia Payne-Gaposchkin.
And it was Cecilia Payne-Gaposchkin who made the truly profound discovery in 1925. Analyzing the Harvard spectra for her PhD thesis, she concluded that stars were composed almost entirely of hydrogen and helium, with heavier elements making up only a tiny percentage.
This was a radical idea at the time, overturning the widely held belief that stars had compositions similar to Earth. Her findings were initially met with skepticism, but was soon accepted, fundamentally changing our understanding of the two simplest elements.
This spectral classification, combined with measurements of stellar brightness, led to another crucial tool, the Hertzsprung-Russell diagram. Developed independently by Ejnar Hertzsprung and Henry Norris Russell around 1910, it plots a star's absolute magnitude, its true intrinsic brightness, against its spectral class temperature.
This diagram revealed clear patterns, with most stars falling along a main sequence. It also showed distinct groups like giant stars and faint, hot white dwarfs. It organized everything.
The HR diagram is more than just a plot. It's a map of stellar evolution. Stars spend most of their lives on the main sequence, and the diagram shows the paths they take as they age and change, evolving into different types of stars. You can see their life stories.
Okay, so we started to understand what stars are made of and how they evolve, but how do we figure out the distances to these incredibly distant objects? This brings us to measuring the universe, the scale of things.
One fundamental method is stellar parallax, that apparent wobble of a star's position as Earth orbits the sun. It's the same effect you see if you hold a finger in front of your face and alternately close each eye. Your finger seems to jump against the background.
The sources mention that Aristarchus, back around 220 BCE, actually suggested that the stars must be incredibly far away because he couldn't detect this parallax with his naked eye observations. Clever deduction. And Tycho Brahe, for the same reason, inability to detect parallax with his precise instruments, used it as an argument against the Copernican Earth-moving model.
Measuring this tiny apparent shift required immense precision. The first successful measurement of stellar parallax wasn't achieved until 1838 by Friedrich Bessel, who measured the parallax of the star 61 Cygni.
Bessel's measurement showed 61 Cygni was about 600,000 times farther away than the Sun. 600,000. This was the first solid rung on the ladder of cosmic distances and confirmed the vast scale of the stars. Other techniques and instruments like the heliometer, used by astronomers like David Gill, were also developed to improve parallax measurements.
But parallax only works for relatively nearby stars. To measure distances to much farther objects, like other galaxies, astronomers needed standard candles, objects whose true intrinsic brightness is known, like knowing the wattage of a distant light bulb.
And this is where Henrietta Swan-Leavitt's discovery in 1912 was absolutely vital. Working again at the Harvard College Observatory, Leavitt studied Cepheid variable stars, stars that pulsate regularly.
She discovered a precise relationship. The longer the period of a Cepheid's pulsation, the brighter the star actually is. Its absolute luminosity, a direct link.
Once Ejnar Hertzsprung calibrated this period-luminosity relationship in 1913, Cepheid variables became incredibly powerful standard candles. Measure a Cepheid's pulsation period, know its true brightness, compare that to how bright it appears from Earth, and bam, you can calculate its distance. This became a key tool for measuring distances far beyond our galaxy, crucial for Hubble later on.
Let's bring it back closer to home for a moment, exploring our own solar system and what else is out there beyond the known planets. Still lots to find nearby.
Our solar system has continued to reveal surprises. Uranus, for instance, the seventh planet, is actually visible to the naked eye and might have been seen as early as Hipparchus in 128 BCE, or recorded by later astronomers like Flamsteed and Lemonnier in the 17th, 18th centuries.
But because it's so faint and moves so slowly, they mistook it for a star. It wasn't recognized as a planet until William Herschel's observation, showing how even nearby objects could hide in plain sight until recognized for what they were. Easy to miss.
The region between Mars and Jupiter also held a predicted but unseen object, suggested by Johann Tischi's numerical pattern, Bode's law. A gap, sort of.
In 1801, Giuseppe Piazzi discovered Ceres using a very precise telescope. He suspected it was the missing planet, but lost track of it after it passed behind the sun. Whoops.
Luckily, the brilliant mathematician Carl Friedrich Gauss, still in his 20s, used Piazzi's limited observations to calculate Ceres' orbit precisely. Genius. Allowing astronomers to find it again on New Year's Eve that year.
Ceres was initially thought to be the missing planet, and estimates of its size varied wildly. We now know it's about 588 miles across, the largest object in the asteroid belt, and classify it as a dwarf planet, massive enough for its gravity to make it round. It's a big deal in the belt.
Speaking of rocky objects, what about meteorites, those stones that sometimes fall from the sky? Their origin was a source of debate for a long time. Rocks from space. Seemed crazy.
In the 1790s, Ernst Chladni studied historical accounts of such falls and examined the stones themselves. He correctly concluded that these stones fall from the sky. that the heat and light shooting stars are caused by atmospheric friction, that they originate from beyond Earth's atmosphere, and that they are fragments of material that didn't form planets. Leftovers.
His ideas were initially met with ridicule, but acceptance grew after well-documented falls, like the one in L'Aigle, France in 1803, provided clear evidence of their extraterrestrial origin. Hard to argue with a field full of space rocks.
Then there are comets, those icy wanderers. Fred Whibble's dirty snowball model became the standard understanding of their composition: ice, dust, and rock, basically.
Early telescopic observations identified comets, and Edmund Halley, using Newton's laws, famously predicted the return of a specific one. More recently, the European Space Agency's Rosetta mission rendezvoused with Comet 67P in 2014, even landing the Philae probe on its surface. Incredible mission.
Rosetta gave us amazing close-ups, revealing the comet's irregular multi-lobed shape, thought to be two smaller objects gently joined together. Like a rubber duck, they said. The mission also confirmed comets are remnants from the formation of the solar system, shedding ice and dust as they approach the sun. Time capsules, really.
And where do these comets come from? The sources point to the Oort cloud, a vast spherical shell of icy bodies far, far beyond the planets, as the source of long-period comets, way out there.
For short-period comets, the source is the Kuiper Belt, a region beyond Neptune populated by icy bodies. Kenneth Edgeworth and Gerard Kuiper speculated about this region, and Julio Fernandez realized such a belt was needed to explain the short-period comets, leading to its confirmation. Pluto lives out there.
Let's talk about the moon's origin, a question that has puzzled astronomers for centuries. How did we get our big moon?
Several theories were proposed over time. George Darwin suggested the moon fissioned from a rapidly spinning early Earth, like it just spun off. Harold Urey proposed the Earth captured a preformed moon, though its size made this seem unlikely. Too big to just grab.
Reginald Daly proposed a giant impact theory in 1946, suggesting a collision knocked material off Earth that then coalesced into the moon. This theory, initially less popular, gained traction after analysis of moon rocks brought back by the Apollo missions showed evidence consistent with a massive impact event. The rocks told the story.
Modern versions of the giant impact theory, supported by Apollo data, suggest a Mars-sized body collided with early Earth. Wham! More recent ideas even propose collisions involving a smaller companion moon of Earth, still refining the details.
Our ability to explore the solar system dramatically increased in the early 1960s with the dawn of interplanetary exploration driven by the US and Soviet Union. The space race fueled it.
Robotic spacecraft, like NASA's Mariner program managed by JPL, began flying past planets, sending back the first close-up images of Venus and Mars. The flyby technique was perfected, allowing spacecraft to get close without the need for complex orbital maneuvers initially. Just a quick look.
A fantastic example of the power of orbital mechanics is Gary Flandra's calculation in 1965. He found a rare planetary alignment in the late 1970s. That would allow a single mission to visit all four outer gas giants, Jupiter, Saturn, Uranus, and Neptune, using gravity assists, slingshotting from planet to planet.
This led directly to the Voyager missions, launched in 1977. These incredible spacecraft completed that grand tour and are now in interstellar space. Still going. Voyager 1 flew past Jupiter and Saturn, providing unprecedented views of Jupiter's moon Io and Saturn's complex rings and moon Titan.
Voyager 2 followed, also visiting Jupiter and Saturn, but continued on to make history as the first and only spacecraft to visit Uranus and Neptune. Amazing feat. Its images of Jupiter's moon Europa hinted at a fractured ice crust, leading to the later realization of a probable subsurface liquid ocean. Water under the ice.
And Europa's likely ocean is now considered one of the most promising places in our solar system to search for signs of life, making it a key target for future missions. Could there be life there?
Further out still, the exploration of Pluto was a long-held ambition, finally realized by the New Horizons mission, launched in 2006 and arriving in 2015, led by Alan Stern.
For decades, Pluto was just a distant point of light. New Horizons, a product of perseverance after earlier mission cancellations, provided our first detailed look at this fascinating world and its moons. Finally saw it up close.
It's interesting that while New Horizons was in flight, Pluto's classification changed. In 2006, the IAU reclassified it as a dwarf planet after other large objects like Eris were discovered in the Kuiper Belt. Pluto remains the brightest object in that belt, though. Still special.
New Horizons gave us spectacular images and data from Pluto and continues its journey into the Kuiper Belt, exploring other icy bodies. Its power source should keep it operational until around 2030. As a poignant detail, some of the ashes of Clyde Tombaugh, who discovered Pluto in 1930, were on board the spacecraft. A fitting tribute.
Mars exploration remains a major focus today. The sources mention the Mars Science Laboratory rover Curiosity, which landed in 2012.
Curiosity is a state-of-the-art mobile laboratory, the largest and most advanced rover sent to Mars so far. It conducts geological experiments to understand the planet's past environment and its potential for habitability. Its operations represent the forefront of our robotic exploration of the red planet. Still rolling.
We've talked about planets, moons, asteroids, and comets. Now let's zoom out even further to the truly massive structures in the universe. Galaxies and the universe itself, the really big picture.
For a long time, those fuzzy patches of light called nebulae were a mystery. William Herschel systematically cataloged deep sky objects, classifying them as either nebulae or star clusters, but their true nature was debated. What were they?
The key question became, were spiral nebulae just gas clouds or star clusters within our own galaxy, the Milky Way, or were they distant island universes, separate galaxies far beyond our own?
William Huggins had used spectroscopy to show that some nebulae were gaseous, displaying emission lines, but the spiral ones were different. Their spectra showed absorption lines, like stars.
The crucial data came from Vesto Slipher, who from 1912 onwards used spectroscopy to measure the speeds of these spiral nebulae using the Doppler shift of their light. How fast were they moving?
He found something astonishing. These objects had incredibly high velocities relative to Earth. Most were redshifted, meaning they were moving away from us at great speed, really fast. Slipher concluded in 1917 that these spiral nebulae were likely external galaxies, reinforcing Immanuel Kant's earlier philosophical idea of island universes.
He noted specific examples like M104 receding at almost 600 miles per second. These speeds were far greater than anything seen within our galaxy, strong evidence they were outside its confines.
Meanwhile, astronomers were also trying to map our own Milky Way. Jacobus Kapteyn initially created a model based on star counts that placed our solar system near the center. Seemed reasonable.
But Harlow Shapley, using the distribution of globular clusters, dense star balls orbiting the galactic center, showed that the solar system is actually located far from the Milky Way center, out in the suburbs, basically.
Then, Bertil Lindblad and Jan Oort in the 1920s proved that the Milky Way is rotating, confirming Shapley's placement of the galactic center towards Sagittarius based on stellar motions. The whole galaxy spins.
We now know our galaxy is a vast rotating disk, though its rotation is slow from our perspective, taking about 225 million years to complete one term, a galactic year.
But linking our galaxy to those distant spiral nebulae required Edwin Hubble. Building directly on Henrietta Leiavet's work with Cepheid variables, Hubble measured the distance to nearby galaxies like Andromeda. In 1924, he definitively proved they were millions of light years away, confirming they were indeed separate galaxies far beyond the Milky Way. Case closed.
And Hubble combined these distances with Vesto Slipher's redshift measurements for these galaxies. In the late 1920s, he discovered a profound relationship. The farther away a galaxy is, the faster it's moving away from us.
This was the observational proof of the expanding universe, now known as Hubble's law. It's not that galaxies are moving through static space, but that space itself is stretching, carrying the galaxies along. Mind-bending.
It's amazing to think about. While the universe is expanding overall, our nearest large neighbor, Andromeda, is actually on a collision course with the Milky Way, expected to merge in about 4 billion years, galactic pileup.
This understanding of expansion led naturally to theories about the universe's origin. Georges Lemaitre, a Belgian priest and physicist, proposed in 1927 that a relativistic universe could be dynamic and expanding. Predicting the velocity-distance relationship Hubble later found, he saw it coming.
And in 1931, Lemaitre proposed the universe began from a tiny, dense point, his primeval atom, which then expanded. This was the seed of the Big Bang theory.
George Gamow, with Ralph Alpher and Robert Herman in the 1940s, developed the Big Bang theory further, calculating the conditions in the very early universe that would allow for the formation of light elements like hydrogen and helium, a process called Big Bang nucleosynthesis, cooking up the first elements.
And crucially, they also predicted that the early hot, dense state of the universe should have left behind a faint afterglow of radiation, an echo of the beginning.
This prediction was stunningly confirmed accidentally in 1965 by Arno Penzias and Robert Wilson using a radio antenna. They couldn't get rid of this faint hiss. They detected a persistent microwave background radiation coming from all directions, the cosmic microwave background, or CMB. The echo was real.
The CMB is light from about 380,000 years after the Big Bang when the universe cooled enough for atoms to form. Originally orange light at about 3,000 Kelvin, the expansion of space has redshifted it to microwaves with a temperature around 2.7 Kelvin today. Very cold now.
The CMB provided incredibly strong support for the Big Bang theory. Later missions like COBE, led by George Smoot and John Mather, detected tiny temperature fluctuations in the CMB, little ripples.
These incredibly small variations represent slight density differences in the early universe, which acted as the seeds for the formation of galaxies and structure we see today. They also offer clues supporting the idea of cosmic inflation.
Cosmic inflation, a theory proposed by Alan Guth in 1981, suggests the universe underwent a period of extremely rapid exponential expansion right after the Big Bang, like incredibly fast.
This theory attempts to solve puzzles, like why the universe appears so smooth and uniform on large scales, even in regions too far apart to have interacted since the Big Bang. How did it get so even? It also explains why the geometry of space seems so flat.
Inflation suggests that superfast expansion smoothed out inhomogeneities and stretched tiny quantum fluctuations into the seeds for structure seen in the CMB. While it explains many observations, the sources note it remains unproven. Still a theory we're testing.
Looking at the large-scale structure of the universe today, redshift surveys mapping the positions of millions of galaxies have revealed that galaxies aren't randomly scattered. Margaret Geller and John Hutra pioneered these surveys starting in 1977, mapping the nearby universe.
Their work revealed a complex, interconnected cosmic web. Galaxies are clustered into filaments and walls surrounding vast empty regions called voids. It shows that the universe has structure on scales much larger than individual galaxies or clusters, like a giant cosmic sponge.
Underlying all these incredible cosmic phenomena are the fundamental laws of physics. Let's talk about the engine powering the stars. Nuclear fusion.
The source of stellar energy was a puzzle for a long time. Early ideas like gravitational contraction couldn't explain the sun's energy output over billions of years. It just wasn't enough power.
The key insight came from understanding nuclear physics. Francis Aston's discovery in 1919 that 4 hydrogen nuclei weigh slightly more than 1 helium nucleus was crucial. Mass goes missing.
When this mass difference is converted to energy via Einstein's EMC7, the amount is enormous. Arthur Eddington championed the idea that stars were powered by nuclear processes. That's where the energy came from.
Hans Bethe provided the detailed mechanisms in the late 1930s. He described the proton-proton chain, where hydrogen nuclei fuse into helium in stars like the Sun, releasing immense energy. And the CNO cycle, important in more massive stars, different ways to cook hydrogen.
This process of creating heavier elements from lighter ones is called nucleosynthesis, and it happens inside stars. Stars are the universe's element factories. We're made of star stuff.
And speaking of Einstein, we can't discuss modern astronomy without his theories of relativity. Changed everything.
Einstein's special relativity, 1905, is built on the principle that the speed of light is constant for all observers, no matter how you're moving. This leads to mind-bending concepts like time dilation, where time passes slower for objects moving at high speeds, and length contraction. Things get weird near light speed.
And it established the speed of light as the ultimate speed limit for anything with mass. As an object approaches light speed, its mass increases and time slows down dramatically. Can't get there.
Then came his general theory of relativity, 1915, which completely changed our understanding of gravity. Instead of a force, general relativity describes gravity as the curvature of spacetime caused by mass and energy.
Massive objects warp the fabric of spacetime around them, and other objects simply follow the curves in this warped geometry, like marbles rolling on a stretched rubber sheet. Einstein's equations link the distribution of matter and energy to the geometry of spacetime. Beautiful math.
It's interesting that Einstein initially added a cosmological constant to his equations in 1917 to keep the universe static, matching the belief at the time. After Lemaitre and Hubble showed the universe was expanding, he called this addition his biggest blunder. Oops. But, as we'll see, it became relevant again. Funny how that happens.
One of the most dramatic predictions of general relativity came from Carl Schwarzschild, who found a solution to Einstein's equations in 1916 describing what happens when mass is incredibly dense.
This solution predicted black holes, regions where gravity is so strong that nothing, not even light, can escape the boundary called the event horizon. No escape.
Black holes were theoretical until observational evidence mounted. The discovery of the X-ray source Cygnus X1 in 1964 was key. By 1973, it was confirmed as an X-ray binary, where an unseen, supermassive object was pulling material from a companion star, sucking stuff off its neighbor.
Calculations showed this unseen object was too massive to be a neutron star, leaving a black hole as the only explanation. Cygnus X1 became the first confirmed black hole, moving these objects from theoretical curiosities to observed reality. They're real.
Radio telescopes also led to the discovery of quasars, quasi-stellar radio sources. These looked like stars but emitted immense energy across the spectrum. Super bright.
The theory is that quasars are the incredibly luminous, active centers of distant galaxies, powered by a supermassive black hole at their core accreting surrounding material. This infalling material forms a superheated disk that emits vast amounts of energy. Feeding frenzy.
Young galaxies are thought to often have these active quasar nuclei. As galaxies age, they become quieter unless galactic collisions supply new fuel to the central black hole. The sources describe the structure, accretion disks, powerful jets, and how our viewing angle determines whether we see it as a quasar, a radio galaxy, or a blazar. Depends on how you look at it.
And then there are pulsars, discovered accidentally by Anthony Hewish and Jocelyn Bell Burnell in 1967 as rapid repeating radio signals. Beep, beep, beep.
Initially, they even briefly wondered if it was an alien signal. LGM, little green men. But Thomas Gold provided the correct explanation in 1968. Pulsars are rapidly spinning neutron stars.
Neutron stars are superdense remnants of collapsed stars, predicted earlier by Bade and Zwicky. They form after some supernova explosions. A rapidly spinning neutron star with a strong magnetic field emits beams of radiation, and we see a pulse whenever a beam sweeps across Earth, like a cosmic lighthouse. Spin, flash, spin, flash.
Now, for all this incredible understanding, the universe still holds fundamental mysteries. Perhaps the biggest are dark matter and dark energy, the stuff we don't see.
Newton's gravity works great in the solar system, but applying it to galaxies and galaxy clusters on larger scales shows something is missing. Things don't add up. Galaxies rotate too fast to their outer regions. Galaxy clusters hold together despite the visible galaxies not having enough mass. There's extra gravity somewhere.
Early hints came from Jan Oort studying the Milky Way and Fritz Zwicky studying the Coma cluster in the 1930s, though their ideas of dark matter were initially dismissed, ahead of their time.
The compelling evidence came from Vera Rubin and Kent Ford in the 1980s, measuring the rotation curves of galaxies like Andromeda. They found the outer stars were orbiting just as fast as the inner ones. That's weird.
This could only be explained if there was far more mass providing gravitational pull than could be seen in visible stars and gas. Rubin calculated that the total galactic mass was about 7 times the visible mass. Current estimates suggest visible matter is only about 1/16th the amount of dark matter. Most of the mass is in Hubble.
So this invisible dark matter, making up about 27% of the universe's content, is inferred solely through its gravitational effects. What is it? That remains a fundamental question. We have no idea, really.
Possible explanations include weakly interacting massive particles, WIMPs, or maybe our understanding of gravity needs modifying on cosmic scales, MOND. As Bill Bryson humorously put it, it's effectively Dunnos, for now, dark unknown, non-reflective, non-detectable object somewhere. Pretty much sums it up.
And then there's the even more mysterious dark energy, discovered in 1998 by 2 teams studying distant Type 1a supernovae.
Type 1a supernovae are crucial because they're considered standard candles. They explode with a remarkably consistent peak intrinsic brightness, reliable cosmic light bulbs. By measuring how bright they appear from Earth, astronomers can calculate their distance.
What the teams found was that distant supernovae were fainter than expected, meaning they were farther away than their redshift would imply in a simply expanding universe. They were too far away.
This staggering finding meant the universe wasn't just expanding. Its expansion was accelerating, speeding up.
And whatever is causing this accelerated expansion is called dark energy. It makes up a mind-boggling 68% of the universe's total mass energy, most of the universe. It acts like a repulsive force, pushing space apart faster and faster. Anti-gravity.
Explanations range from modifications to gravity, or perhaps it's related to Einstein's cosmological constant, representing the energy of the vacuum itself, with virtual particles creating negative pressure. As Brian Schmidt, one of the discoverers, is quoted, it implies there is some unknown form of energy that is ripping the universe apart.
Yikes! A more recent and very exciting breakthrough connects directly back to Einstein's general relativity, the detection of gravitational waves. These are tiny ripples in space-time caused by massive, accelerating objects like colliding black holes or neutron stars. Space itself shaking.
The LEGO experiment detected gravitational waves for the first time in 2016. The LIGO detectors are massive laser interferometers with arms miles long, designed to detect incredibly tiny changes in distance caused by a passing gravitational wave. Unbelievably sensitive.
The sensitivity is astonishing, detecting distortions smaller than an atomic nucleus. This opens a whole new window on the universe, allowing us to hear violent cosmic events that are invisible in light, like the merging of black holes. A new sense for astronomy.
All this progress has, of course, depended on developing incredible tools. Observatories, both on the ground and in space, are our eyes on the universe.
For ground-based observatories, site selection is key, needing clear, dry, still air and low light pollution. Places like northern Chile, home to ESO, and Mauna Kea in Hawaii were chosen after extensive surveys.
Yep.
Got to get above the gunk.
Ground telescopes have become highly sophisticated. ESO's New Technology Telescope in 1989 pioneered innovations like flexible mirrors, whose shape is adjusted by computer-controlled actuators to compensate for atmospheric distortion. Adaptive optics. Techniques now standard in large telescopes, making ground-based views super sharp.
The future involves truly enormous telescopes. The Extremely Large Telescope, EELT, in Chile, expected completion 2024, will be the largest optical telescope ever, with a 129-foot segmented primary mirror. Huge. Its resolution will be 15 times sharper than Hubble's. Can't wait to see what it finds.
Beyond just collecting light, capturing it has been vital. Astrophotography, pioneered by figures like John Draper and his son Henry in the mid-19th century, allowed astronomers to record faint objects over long exposures, soaking up light.
David Gill at the Cape Observatory was a major proponent of astrophotography, producing detailed star catalogs photographically and contributing to ambitious mapping projects like the Carte du Ciel. He also refined the use of the heliometer for parallax measurement, a multi-talented guy.
But Earth's atmosphere distorts light, causing stars to twinkle and limiting clarity, what astronomers call seeing, annoying wobble. Lyman Spitzer Jr. was a tireless advocate starting in the 1940s for putting telescopes in space to escape this atmospheric blur. Get above it all.
His advocacy led to projects like OAO2 and eventually the Hubble Space Telescope, HST. Hubble was designed as a large reflector, planned for servicing in space. Smart move.
Famously, Hubble had a manufacturing flaw in its mirror, initially causing blurry images. A tiny error, big problem. But because it was designed for servicing, astronauts were able to install corrective optics, essentially space eyeglasses, restoring Hubble's vision to its full potential. It has since been transformative for astronomy, including refining measurements of the universe's expansion rate. An icon.
The next generation is already here, the James Webb Space Telescope, JWST. Orbiting the Alto-Lagrange point, a stable spot far from Earth, JWST is designed to see the universe primarily in infrared light.
Infrared is crucial for seeing the light from the very first stars and galaxies, whose light has been redshifted by the universe's expansion all the way into the infrared. Peering back in time, JWST has a massive, segmented beryllium mirror and is incredibly sensitive. Imagine detecting the heat of a bumblebee on the moon. That's sensitive.
But our view isn't limited to visible or infrared light. Carl Jansky's accidental discovery of extraterrestrial radio waves in 1931 using a homemade antenna opened up radio astronomy. A completely new window on the universe, heard static from space.
Grote Reber followed with the first radio sky survey. After WWII, radio astronomy flourished, leading to the detection of the 21-centimeter hydrogen line by Ewan and Purcell in 1951, a crucial discovery for mapping the spiral structure of our own galaxy using cold hydrogen gas.
And moving to even higher energies, X-ray astronomy began in the 1960s with balloon and rocket flights. Riccardo Giacconi's team detected a diffuse X-ray background in strong sources near the galactic center, leading to the discovery of X-ray binaries like Cygnus X1, seeing the really hot, violent stuff.
NASA's Chandra X-ray Observatory continues this work, studying active galactic nuclei powered by supermassive black holes and mapping the X-ray background in unprecedented detail. Using different wavelengths gives us a much more complete picture of cosmic objects and events, the multi-wavelength universe.
With all these amazing objects and phenomena out there, the question naturally arises, are we alone? This leads us to the search for life beyond Earth, the big question.
A key working assumption in this search is the Copernican principle, formalized by Hermann Mondi. It suggests that Earth is not special. It's likely an average planet around an average star in an average galaxy. We're not the center of everything.
If that's true, given the sheer number of stars and galaxies, it seems statistically probable that life could exist elsewhere. Thinkers like Carl Sagan have pondered this deeply. Echoing earlier questions like Albertus Magnus asking in the 13th century, do there exist many worlds? People have wondered for a long time.
One major approach is the search for extraterrestrial intelligence, SETI, often using radio telescopes. Cocconi and Morrison suggested in 1959 that civilizations might signal near the 21-centimeter hydrogen line, a universal frequency, the cosmic water cooler.
This inspired Frank Drake's Project Ozma in 1960, listening for signals from nearby sun-like stars. No signals were detected, but it kick-started the field. Drake later formulated the famous Drake equation to estimate the number of intelligent civilizations in the Milky Way. How many are out there?
The WOW signal, picked up by Jerry Amen in 1977, remains a famous, unexplained transient radio signal in SETI history. Still a mystery.
There have also been efforts to send messages outward. Carl Sagan and Frank Drake designed the Pioneer plaque in 1971, which included information about humanity and Earth's location, using the 21-centimeter hydrogen line as a universal ruler, a message in a bottle thrown into the cosmic ocean.
And in 1974, the Arecibo message, a binary-coded message about humanity and our place, was broadcast once from the Arecibo radio telescope, just once, aimed at a distant star cluster.
Beyond looking for intelligent signals, robotic missions within our solar system have searched for signs of life, even microbial. As we discussed, Europa's subsurface ocean is a prime candidate due to its liquid water and potential energy sources. Maybe something swimming down there.
But the biggest breakthrough fueling the search for life has been the discovery of exoplanets, planets orbiting other stars. This was a long-held dream, finding other worlds.
The first confirmed exoplanet, 51 Pegasi b, was discovered by Michael Mayer and Didier Queloz in 1995. It was a Jupiter-mass planet orbiting a sun-like star, really close in, a hot Jupiter. Found using the radial velocity method, detecting the star's wobble from the planet's gravitational ton using sensitive spectrographs, tiny wobbles revealing giant planets.
Another powerful method is the transit method, looking for the dimming of a star's light as a planet passes in front. NASA's Kepler Space Observatory, launched in 2009, used this to identify thousands of exoplanet candidates, staring at stars, waiting for dips.
Kepler and ground-based telescopes have revealed a wide variety of exoplanets, hot Jupiters, super-Earths, mini-Neptunes. Finding truly rocky, Earth-sized planets, especially in their star's habitable zone where liquid water could exist, remains challenging, but is a key goal. The hunt for Earth 2.0.
Astrobiologists focus on identifying worlds with conditions suitable for life as we know it, liquid water, carbon chemistry, protective atmospheres. The sources note that only a tiny fraction of candidates are in the habitable zone with Earth-like prospects, and many are still larger than Earth. Finding a true twin is hard.
A future step will be analyzing exoplanet atmospheres for biosignatures, like oxygen, which on Earth is a product of life, sniffing the air of other worlds.
The search for life in all its forms is perhaps the ultimate test of the Copernican principle and our place in the cosmos. As Carl Sagan put it, we are almost certainly not the first intelligent species. The search pushes us to consider the vastness and the possibility that humanity might not be unique. Are we special, or just one example among many?
One final area from the sources that brings together many concepts is the detailed process of how stars actually form. Where do stars come from?
Stars aren't just born out of nothing. They condense from giant molecular clouds, GMCs, vast, cold clouds of gas and dust scattered through interstellar space, a concept studied by Bart Bok and Lyman Spitzer Jr.
The process begins with denser regions within these clouds called Bok globules, collapsing under their own gravity. Things start clumping together. This transformation from cloud to protostar and embryonic star happens deep inside these opaque clouds and takes millions of years, making it hard to observe directly. Hidden nurseries.
Astrophysicists rely on complex mathematical models based on physics to simulate this process. Considering gravity, turbulence, and magnetic fields within the collapsing cloud, computer simulations help us see.
As the protostar forms over millions of years, about 10 million for a sun-like star, it accumulates mass. It often develops powerful jets from its poles that widen and push surrounding gas away, blasting stuff out.
Eventually, a stellar wind clears the remaining cloud material, revealing the young stellar object. The star emerges. The subsequent evolution depends heavily on mass.
Giant stars, over 8 solar masses, start hydrogen fusion early and live fast, bright lives. Burn bright, die young. Smaller stars, less than 8 solar masses, are pre-main sequence PMS stars. They go through a longer contraction phase, powered by gravity, for maybe 100 million years for sun-like stars, until their core gets hot enough to ignite fusion and join the main sequence. Takes them longer to turn on.
Larger PMS stars, 2 to 8 solar masses, briefly become rare blue dwarfs before the main sequence.
And crucially, during the PMS phase, a spinning disk of leftover material surrounds the young star. While some is dispersed, the remaining material, especially around smaller stars, is where planets form. Gas giants first, then rocky ones closer in. Star formation is intimately linked to planet formation. You get stars, you probably get planets too.
So let's zoom back out and pull together some of the key lessons from this incredible journey through the astronomy book. What have we learned?
First, the history shows us that our understanding of the cosmos is constantly evolving. It's not fixed. We've moved from a small, geocentric, seemingly static universe to one that's vast, heliocentric, dynamic, and expanding, filled with billions of galaxies. What a change in perspective.
Second, technological innovation has been the engine of discovery. Tools matter. From the telescope to spectroscopy, astrophotography, space telescopes, radio X-ray astronomy, and gravitational wave detectors, each new tool has allowed us to see farther, deeper, and in entirely new ways, fundamentally changing what we know.
Third, key theoretical frameworks from figures like Kepler, Newton, Hubble, and Einstein have been essential, providing the physical laws that explain the observations. Ideas matter too. Their work, often building on the meticulous data gathered by others, created the conceptual maps that guide our understanding, connecting the dots.
Fourth, the universe is far more diverse and dynamic than early astronomers imagined. It's not just boring points of light. We've discovered an incredible menagerie of objects, different stars, galaxies, black holes, pulsars, quasars, comets, asteroids, and violent complex processes shaping the cosmos. It's a wild place.
Fifth, our place in this vastness seems increasingly humble, reinforced by discoveries like the sheer number of exoplanets. The Copernican principle holds strong, suggesting we are likely not unique, which opens up profound questions about life elsewhere. Makes you think.
And finally, despite immense progress, fundamental mysteries remain, particularly regarding dark matter and dark energy, which make up the vast majority of the universe's content. These unknown components are forcing us to confront what we don't understand about the fundamental physics governing reality. We still don't know what most of the universe is.
It's a story of continuous discovery, building on centuries of human ingenuity and curiosity.
We've journeyed from clay tablets predicting cycles to gravitational wave detectors listening to colliding black holes. Our understanding has been constantly challenged and reshaped by new observations and revolutionary ideas.
We went from believing Earth was the center of a small cosmos to mapping a vast, structured, expanding universe of billions of galaxies, each a complex system with billions of stars, many with planets. The scale is just staggering.
We've grappled with fundamental forces like gravity, the engine of stars and nuclear fusion, and the baffling repulsive effect of dark energy. We've developed incredible tools to see the unseen and measure the immeasurable.
But as we've seen, the more we discover, the deeper the mysteries can become. Dark matter and dark energy are humbling reminders that we are still very much on the frontier of cosmic understanding. Lots more to learn.
Okay, here's where it gets really interesting, though. If everything we've learned, all these technological leaps and theoretical breakthroughs, still leave us fundamentally misunderstanding 95% of what the universe is made of, the dark matter and dark energy. What fundamental physics are we still completely missing? What new discoveries lie just beyond the reach of our current instruments and theories?
It's a profound question. The discoveries laid out in these sources are monumental, yes, but they also open up even vaster territories of the unknown. It tells us the journey of cosmic discovery is far from over, not by a long shot.
Absolutely. With powerful new telescopes like the ELT and JWST operating and gravitational wave astronomy just beginning, how might our picture of the universe be fundamentally transformed again in the next few decades? The story of astronomy is a story of perpetual revelation, always changing.
It truly is, and a testament to the enduring human drive to understand our place in the cosmos. We just keep looking up.
If this deep dive into the universe from the Astronomy Book has sparked your curiosity about any of these topics, from ancient calendars to dark energy or the search for life, we encourage you to explore them further. The book itself is a great starting point, or you can delve into resources about specific areas that caught your interest.
And join us next time for another deep dive into fascinating topics.